All right, welcome back. Today it's October the 14th, and we're gonna finish up chapter 7. All right, so let me go to my notes, my instructor's notes. So here you have the last two slides. The last time when we met, we talked about tautomerization. I need to share the screen. Hold on. All right, so yeah, last time when we met, we talked about tautomerization and how, depending on the transformation, if it's hydroboration on a triple bond, it will give you an enol that will transform into an aldehyde. And if you have the same triple bond or alkyne and you do hydration, it will give you an enol that will transform into a ketone. All right, so terminal alkynes form aldehydes and internal alkynes form ketones. So, all right, and so the keto form could be an aldehyde or a ketone final product. Okay, then alkynes, as you know, can become cis double bonds by the use of Lindlar's catalyst. Lindlar's, it's a catalyst that has been poisoned with lead. So it's palladium poisoned with lead, and that weakens palladium a little bit, so that if you didn't have Lindlar's and you just add palladium, it still do the same thing, sin addition, but also will reduce it all the way. You will have a mixture of the cis pentane and the pentanol. In this case, it will reduce it all the way to a single bond, and that's why Lindlar's is so awesome in the way, because it stops right at the double bond, so you can selectively just choose to reduce one pi bond instead of two. So in another sense, what I'm saying is, if you have palladium, you will have this, and you will have a mixture of this. And I don't know the percentages, but you will definitely have a mixture, and that's undesirable. And so, yeah, that's why Lindlar's is good, because you get rid of the double reduction. And so, even with 1 mole of hydrogen gas. Now, I'm going to teach you the anti-addition now. If you have a metal like sodium or lithium in the presence of liquid ammonia at -78, you get to put those two hydrogens in a trans fashion. So, depending on what you want, if you want to have it cis, you use Lindlar's. If you want to have it trans, you use sodium or lithium, one of the two metals, in the presence of liquid ammonia. Liquid ammonia, you're going to see here on the mechanism that it's what provides these two protons. All right. All right. So the mechanism is shown here. Notice that this is a radical reaction. It's a radical mechanism. And so this is the first time we're going to see something like this. And so we said that for a normal mechanism, a full arrow represents 2 electrons. So in other words, each part of the arrowhead represents an electron. So that's 1 electron. This is 2 electrons. So for radical reactions, we use a half an arrow and that represents one electron. All right, so that's what you see here. All right, so notice that when you do radical reactions, you have what is called homolytic cleavage on the bond that is breaking. So the sodium or lithium radical is a radical, but it's also natural sodium or natural lithium in its ground state or metallic state. This triple bond here is going to break in exactly half. So 1/2 goes to this side and the other half goes to that side when it's in the presence of the sodium electron. So sodium simply gives up that electron, and now notice that this here represents that 2 electrons are going to reside in that carbon. Those 2 arrows, that's what that means. And that's what you see here. These 2 electrons are now on this carbon, and 1 electron went to the carbon on the left. It's right here. And so the carbon with 2 electrons gets a minus charge. This is an ion. This part is an anion. And this part right here is a radical. So that's why you call this, well, not that whole part, just this part. That's a radical. And so that's why you call this a radical anion. Very like special type of intermediate. All right, so once you have a base, now the anion part becomes a nucleophile. It's also a base. So in the presence of a proton source, the base is going to grab that proton. And so now notice that this arrow is represented with 2 electrons. So it's a full-headed arrow. It's going to grab that H, and the 2 electrons here that is forming this one are going to be transferred to the nitrogen. Also notice that the byproduct of the first step was sodium plus, because now that's an ion that is floating in solution doing absolutely nothing. It's a spectator ion and it just floats in solution. Flow away, sodium, flow away. And then so now this anion now gets a hydrogen. See that? And then sodium comes back, more sodium. So you have to have at least 2 moles of sodium. It's not set here, but there should be 2 equivalents at least of sodium, because 1 gets the reaction started, puts 1 H here, and this is liquid ammonia. H, NH2 is ammonia. All right. Yeah, ammonia, that stuff that people use to clean up pools that has a particular smell. And if you take a whiff of ammonium hydroxide, which is ammonia in water, oof, it can really open up your nostrils. Sometimes they use that and they put a little bit of cotton on a cotton ball. They put a little ammonia to like wake up people that are fainted or something like that, because it's really strong. I don't like it. So your second sodium comes and plays a role again in adding that one electron to this carbon. And so, oh no, why should I do this? Now I cannot erase that electron because, oh, there you go. Because I feel like Zoom is slowing down my computer a little bit. All right, so sodium simply gives up that electron, like if it was ice cream, just gives it up and puts 2 electrons right there. Now it has 2 electrons in a charge. And so again, ammonia. So you have plenty of liquid ammonia is the solvent of this reaction. These 2 electrons now are going to grab this H, and the 2 electrons here from this bond are going to be transferred to the nitrogen. And notice that because you had a double bond already in place, it was geometrically impossible to rotate around these 2 double bonds. It's locked. So the configuration stays like it is, and you end up with trans additions of hydrogens. So this is one of the early examples of how to do a hydrogenation without even needing hydrogen gas. Sometimes people have used also, I've seen reactions of hydrogenation where they use this is cyclohex 1,3-diene, and these protons are very likely to be abstracted or grabbed, and you make benzene. And so the driving force is here will be to make benzene. And so now you're seeing 3 types. You see the hydrogen gas reductions, the metal and liquid ammonia reductions, and then there's this one, the cyclohex 1,3-diene reductions to make benzene. These ones were the early ones when people didn't have hydrogen gas capabilities in the lab, but now we do. All right, so you don't need to know this for the exam or anything. I was just telling you a little bit of history about reductions. And then, of course, there's one more type of reaction you can do with alkynes, and that's an alkylation reaction. What do they call alkylation reaction? Because you put in an alkyl group attachment. Notice that we're putting that new group there. And so to do this, we use the acetyl anion. This is an acetyl anion, where what is the pKa of that proton? Anybody remember?
Isn't it around 25?
25, very good. Yes, so 25, so it's mildly acidic, and it's acidic enough. So if you have a strong base, like sodium, this is called sodium amide. So sodium amide, some people say sodium amide. You pronounce it the way you want it, and I pronounce it the way I want it too. That's why I joined chemistry, because when we teach chemistry, there's no real pronunciation when it comes to chemicals. Like in the US, we say beta. The British, they say beta. So who's right? Both. Nobody's right or wrong. You can just pronounce the things the way we want it. All right. So 1 pentine. So this is. So I'm gonna show you this synthesis in a minute. But this acetyl anion came from the protonation with a strong base, and sodium amide is a very strong base. It came from ammonia. So here's your spectator ion, sodium doing what? Absolutely nothing in the reaction. So this is plus and this will be minus. So the double bond, the 2 electrons grab the H, and these 2 electrons are now transferred to the carbon, and now you have 2 electrons in a minus charge. And because it's no, it's not acetyl. It's not acetyl. This is not acetyl. Acetylene. That's what it is. Acetylene anion. That's right. Please correct me there. That is called as an acetylene anion because it came from acetylene. It came another nickname that the triple bonds used to have are acetylene. So once you have this acetylene anion, you can do what is called an SN2 reaction. We're going to learn those very, very soon in chapter 9, which in my opinion is the toughest chapter for part 1 of organic chemistry. And you're getting closer and closer, but that doesn't mean you cannot master it. You will master it. All right, so notice that in an SN2 reaction, it's called an SN2 because you have a substituted nucleophilic bimolecular reaction. The 2 means bimolecular, so 2 molecules collide. And so you have a nucleophile. Now your nucleophile is here. Your nucleophile is the biggest bully here. It's going to go and attack the carbon that is partially plus. So it's E minus towards E plus. This carbon is your E plus because it holds the bromine, the leaving group. The bromine is called a leaving group. All right. And so this acetylene ion comes and attacks this carbon and kicks off the bromine. They call this backside attack. So the SN2 you're going to learn is a backside attack with 100% inversion of configuration. So if you have an S, it flips it to an R. That's what this means. If the carbon has been hit, it's chiral, it will flip it. In this case, this carbon right here is not chiral, so we don't have to worry about that. But if it was, yeah, it'll go from S to R or from R to S. So this nucleophile attacks, kicks off the bromine, and now you put an alkyl group here. Notice, count your carbons. You have 1, 2, 3, 4 carbons on the left side. So 1, 2, 3, 4 carbons on the left side. And then your new alkyl group is 1, 2, 3 carbons long. So you have 1, 2, 3 carbons long. So the new bond is right there. And the bromine is your counter ion now. Floating around with whom? With this sodium that was here. It's gonna navigate, they're gonna navigate together in the solution. All right. And that sodium came from the sodium amide part. Okay. So, all right. So here's a scheme. This is not requiring a reaction mechanism. So here you have one pentyne. You have a terminal. This is what is called a terminal alkyne. The pKa of this H is 25. So we said this sodium, I like to take it out. So because if I don't do that, I really don't know how to start this reaction. So I'll simply just take that sodium. Yeah, you look cool, but you're doing nothing. And then I can reveal my base. Now this base, this is an acid-base reaction. And I remember when we talked about chapter 2, when we're doing pKa's, remember I mentioned that acid-base reactions are the first type of reaction that happen in nature. So I said that we have acid-base reactions followed by nucleophilic reactions, which are actually Lewis acid bases. And if it's neither one of those two, it might be a redox reaction. Then we have the rearrangement reactions, like sigmatropic rearrangements. We're going to learn that in chapter 8 with the Diels-Alders. And then finally, we'll have radical reactions. So I'm going to write them down. So 5 types of reactions in organic chemistry. 1, acid-base, nucleophilic, like the SN2. But what happened to the SN2 or SN1? Nucleophilic reactions are base type of reactions. So they fall kind of in the same category, but they're not directly acid base per se because there are no protons involved. But there's nucleophiles, there are electrophiles, just like this. This reaction, you have a nucleophile and you have an electrophile right there. Okay, and then the third type, if it's neither one of those, is redox. The fourth type, redox, you have one that oxidizes, one that reduces, and that's by sharing electrons or gaining or losing electrons. Then the fourth type is what I call rearrangements. And here we're going to find Diels-Alders sigmatropic rearrangements, where you just move bonds, and they could be moved. They could move based on heat applied to the reaction, or if you add UV light, like photochemical reactions, they fall into this category. They are completely different than acid bases or nucleophilic or redox. And the last type is now you've seen a radical reaction. If you know these 5 types of reactions, you know organic chemistry. All right, so that's your goal. If you know all these type of reactions, you could teach organic chemistry, because this is what life is about, these 5 types. Nothing else. So life is simple. We just make it complicated. So very good. So let's go to. Oh, I haven't finished this. So the sodium amide grabs the H from the 1-pentyne, forms your. This is an anion. Your acetylene anion, and now this guy is gonna go and it's gonna kick. It's gonna attack the carbon that it's holding the bromine. That's the leaving group. The leaving group is gonna go out. Boom. You're not paying rent. Get out. Takes him out. And now notice that this becomes 3-heptine. The carbon chain has increased by 2 carbons because we had 2 carbons there. That is alkylation. 2 more carbons added to the chain. All right, very good. Any questions before we switch to the worksheet? Anybody has a question? Quick questions. All right, so notice that now, believe it or not, you can do more than 1-step synthesis, and that's the challenge for you. So notice that it says here, reactions of alkynes. Prepare pentyne from ethine, which is acetylene, in several steps. So we want to go from, this is the starting material, ethine, 2 carbons on a triple bond, and you want to go from here to pentyne. So this is 1, 2, 3, 4, and 5. Pentyne. So here's where chemistry or chem becomes tough. Your ability to synthesize now. And now, by putting all these reactions, new reactions that you have learned together on a list, you are able now to dissect and completely, make this happen. All right, so what would be the first? So you can think backwards or you can think forward. I'm going to teach you thinking forward first, but in the future, I'm going to start teaching you how to think backwards. All right. So what do I start? Notice that I need to put, what is new? What is new here? Let's see what's new here. So on carbons 2 and 3 here, I see a methyl group that is new, that is not here on the starting material. This is it. And I also see on carbons 4 and 5, they have an ethyl group. All right, from what you're seeing, what would be the first step? What would you use to do the first step? And actually, we need 2 steps for this synthesis. All right, what would you use to do the first step? Anybody? Hint, we need to deprotonate one of those H's. Come on, help me out. No, this is a double alkylation. Let me write this down. Note. Double alkylation. The 2 steps could be reversed and still get the desired final target. So what do I start? Help me out. Come on. What are we putting in? Let's say I want to put the ethyl group first to make my intermediate a little bit heavy. with the molecular mass, what would you add? I'll wait. Come on, someone there. Brave soul. This wonderful morning. Finally, we see the sun a lot now. How about sodium amide? What's that gonna do? It's gonna deprotonate one of those two H's. And if I add ethyl bromide, that is my SN2 reaction. That takes me here. Then
how did you get the ethyl bromide?
The ethyl bromide? Yeah, because now you see that I have an ethyl group here. You see that? I have an ethyl group right there, carbons 4 and 5. So I know that this reaction requires having 2 carbons additions. So here's carbon 4 and 5. And then I need a leaving group. That's my leaving group.
Yeah, but how come, like, it's bromide? How come it's not something else?
Oh, gotcha. No, you could have, that's my choice. You could have say ethyl chloride, ethyl iodide, ethyl tosylate. We haven't learned the tosyls yet, but those are good leaving groups. I got it. I got what you mean. Yeah.
Sorry.
No, that's fine. You could also let's see. I'm thinking no, this molecule is too small for putting an alcohol and adding an acid to make water as a leaving group. That's another way of making good leaving groups. But yeah, so choose your leaving group. So your leaving group could be any halogen or a mesylate. We're gonna learn those later. Don't worry about it. I'm not gonna teach you. I'm not gonna quiz you on this. Or you put a mesylate group or a tosyl group. We're gonna learn those. Those are good leaving groups. All right. So for now, you know the halogens. So stick with the halogens. Now let me tell you something about halogens. Iodine reacts better than bromine and reacts better than chlorine, but sometimes iodines are too reactive and chlorines require heat. So whenever I choose one, I choose the boy in the middle, the bromines. The bromines are almost always the best, in my opinion, of the halogens, the best leaving group, because they're not as picky, Oh, you don't need to give me too much heat. I can do the reaction. So bromines are really good. They're intermediates in strength or capacity of leading. So bromines are the best. So you deprotonate this H. You put the minus charge here, and this goes and attack here, right, and kicks off the bromine. And now you have that. Actually, not from that carbon, but if I'm gonna be really to not confuse you, it'll be the carbon here. This is the one, but you just flip it and it's the same thing. And you go like that. And that's what you have here. All right. And then what do I need on the next one? Same base, right? Sodium amide, and what else? How do I put a methyl group there? You got this. Come on. Ethyl bromide was the first step. What would be the next step? All right, come on. Methyl bromide will be my choice. And now, once you made the minus charge here, that's going to attack here and kick this one off after you deproton ADH. All right, but I'm going to delete these charges because they are confusing if I leave them like that. I'm just telling you what's happening. And so now this puts carbon 1 there on the final product. You see it? And so this was always carbons 2 and 3 here. So we put 4 and 5, and then we put carbon 1. So right here we have carbons 2, 3, 4, and 5 made. You see that? So that's how you build molecules. And this is a 1-2 steps, 1-2 punch. All right. You could have also reversed this, the 2 steps could have been reversed and still get this the desired final target. All right. Okay, let's see if you help me out with the next one. It says prepare pentan 1-ol from pent 1-ine in several steps. All right. So let's see. We're gonna start from pent 1-ine. So that's 1, 2, 3, 4, 5. This is pent 1-ine. All right. And I want to get to pentanol or pent 1-ol. 1, 2, 3, 4, 5, and the OH. This is pent 1-ol. All right. So let's see what's new and what's different. All right, check this one out. You have 1, 2, 3, 4, 5 carbons, and here you have 1, 2, 3, 4, 5 carbons. So the carbon skeleton is the same. The only thing we did was to reduce that triple bond. We went from a triple to a double. What I'm envisioning is making this from a triple to a double and making an alcohol. How can I go from a triple to a double? What will I use to make, say, this? 1, 2, 3, 4, 5, double bond, H here and an H here. I'm gonna do a syn addition. You got this. This is from last milestone. Come on, what is that?
A Lindo catalyst?
Yes, very good. You need hydrogen gas and Lindlards. And this, I hate when my arrow is short to what I have it on the top. So this. Like that. That's much elegant. All right. And so now I have an alkene and I want to turn it into a primary alcohol. What is the name of the reaction that I will use to do this transformation? And I'm going to delete these H's so you can see it. Sometimes these H's are too much. How would you go from the middle to the right?
Would it be hydroboration oxidation?
Yeah, very good. That'll be hydroboration oxidation. And so this is an anti-Markovnikov event. And here now you started to combine new knowledge of triple bonds with all knowledge of double bonds. And here is your ability to hold information as a student. This is what makes OCHEM tough. I'm just gonna say it like that, but not impossible, not under my watch, because I'm always going to encourage you that I'm gonna tell you, you are the best. You can do this. Always. I'll be your coach. All right. So, and you can do it. I know you can do it. But yeah, this is the hunting process of OCHEM. All reactions are always going to hunt you because you will need them. That's your arsenal. They can hunt you, or they could be your best friend, and you can say, oh, that is my arsenal of reactions. That's what I bring to, those are my weapons to war. I'm going to bring them on all the time. All right, so let's this slide here is a little summary of what we have learned in terms of synthesis. Okay, so let's just give the final product that happens here and the reaction name. All right, notice that the first reaction, and they all have the same reactant or starting material, but1-ine. So I'm going to switch it right now. Let's do the first reaction. Notice that I have 2 moles of HCl. What would I make? And what's the name of this reaction? First of all, what would be the name of this reaction? Start with an H. All these reactions start with a letter.
Hydrogenation.
Yeah, this is hydrohalogenation. So in hydrohalogenation, count your carbons. You have 1, 2, 3, 4 carbons. So you go 1, 2, 3, 4 carbons. Where will this, so you have an H here. Where will these H's go? These 2 H's. To carbon 1 or carbon 2? If this is a Markovnikov driven reaction.
Are you saying it's 2 H's because there's 2 moles?
Mm-hmm. Yep.
Right.
So the first H will make it a double bond. Let's do it stepwise. The first HCl makes this. You see that? The second one, the second mole of HCl, come back here, red. The second one will put another H here and another chlorine there. Haha, how cool is that? All right. Next reaction. What would be the name of that reaction?
Hydroboration.
No. All I see is halogens. So it's halogenation. All right. The question I have here, what do we get? All right, so let's start with the 4 carbons on my skeleton. 1, 2, 3, and 4. And there's a hydrogen in there. I'm gonna draw it. So let's say I draw it here. Where would the bromines go? So carbons 1 and 2. You have both. The first one, again, is like this. So you have 1 here and 1 here. That's the first mole of bromine used. They go anti. And then the second one, 1 here and 1 here. That is halogenation. All right. So what is the next? We have 4 minutes. What is the next reaction name? Remember this dude? Mercury sulfate. I don't think this stuff does anything to the reaction. I said that at the beginning. There's no involvement of that. Probably the person who did this.
Hydration?
It would be hydration. The first time this was used was contamination. It was contaminated with that. Because I don't see the use. Hydration. This would be hydration. And I'm gonna say a little parenthesis, hydration with tautomerization and everything that is part of this nation ends in Asian. Tautomerization. Yes. Sorry, saying the word Asian at the end, it's just sounds like I'm rapping sometimes. But I'm not a rapper, I promise you. I cannot rap. I wish I could. But I rock and roll though. I'm so sorry. That was bad. Bad. 1, 2, 3, 4 carbons on my main skeleton. All right. If what would be the product? The product here. Where would the OH go on the once the first double bond is made? So you're gonna end up with this. Remember, this is your enol. That's your intermediate for that reaction. Would that enol make an aldehyde or a ketone? Remember the. Oh, let me draw it on the left side. So let's use it. So I'm gonna make this. So, come on, erased. And so click going something. You're gonna go from the enol to the keto form. What would be the keto form of that? Well, let's do this. And then you'll know the answer. So 1, 2, 3, 4 ketone will go there, and you'll have 3 hydrogens on that carbon. 1 from the alkyne and 2 from the 1 from the acid and 1 from the enol. Those are the 3 hydrogens where they came from. Let's write it down. 1 hydrogen from the alkyne, 1 hydrogen from the acid, and 1 hydrogen from the enol. All right, let's finish this one up. Give me 1 minute. What is the name of this reaction? Starts with an H. You see this? You see that? And you see this. You know this.
Is it hydroboration?
Yes, very good, Kylie. Hydroboration. And I'm gonna say here with tautomerization because it's a triple bond. If you say hydroboration, it's fine. I'm just saying that this is gonna tautomerize. So you're gonna get this guy. Oh, double bond here. 1, 2, 3, 4 with an OH here, and that's going to tautomerize. So this is going from the enol to the keto, and the keto form will be 1, 2, 3, 4 an aldehyde. Maybe I fix this so that it looks like the one on the right. Hold on. So here you have that. So you're going from the enol to the keto, and it prefers the aldehyde. All right, very good. We'll finish the mechanism on Friday, and then we will start chapter 8. Thank you. Let me turn off the recording if I can.